Hey everybody, welcome back to chemistry. And so we're almost at the end of chapter 7. And so one of the things I need to talk to you about is something called kinetic molecular theory. And what that is a theory that explains the properties and behavior of gases. And so this is covered in section 7.10 in your book. And so before I talk about the theory, let me just kind of remind ourselves what the difference is between a theory and a law. So we've encountered a lot of laws as we've been going through this chapter in chapter 7. So for example, Boyle's law and Charles' law and so on and so on. So what you may remember is that a law is a summary of data. So let me give you an example of this. So let's say that you had a sample of oxygen gas. And let's say that you took this sample of gas and you reduced its volume in half. What you would find is that the pressure would double. Now, let's say you did the same kind of experiment, but you changed the gas. Let's say you did the same experiment with a sample of carbon dioxide gas. Well, if you have the volume of that gas, its pressure will double. So let's say you did helium, you would get the same result. If you have the volume of the gas, its pressure would double. And that would be pretty much true for all gases that exist. And so what we can do is sort of summarize those observations into a law that basically says that for all gases, if you halve the volume of that gas sample, you will double the pressure. And so that is a law, and we stick a person's name to it to help us remember that. So that is an example of Boyle's law. Now, one of the things about laws that you can see with gases is that we make observations for these laws with our own eyes and with apparatus that we have readily available. And so what we say is that these laws describe properties that we can sort of easily see, so they are at the macroscopic level. Now, what I want to do is talk about what a theory is. A theory is an explanation of observations and data. So one of the things you'll see is that in chemistry, our theories usually are at the levels of molecules. So they're at a very small level that we cannot see with our unaided eye. So we are looking at the microscopic level. So here, the kinetic molecular theory is a theory that is at a very microscopic level. We can call it a molecular model if we want to, and we're going to use that to explain the macroscopic properties and behavior of gas molecules. So let me just give you a quick example of that. And so one of the properties of gases is that they are compressible, which means is that you can pretty easily reduce their volume. So that can be explained if we include in kinetic molecular theory the idea that gas molecules are very far apart from one another. So if the gas molecules are far apart from one another, then it's pretty easy to imagine that we can press the gas molecules together to compress it. So what we're going to do is we're going to make some specific assumptions and postulates about gas molecules and then use them to explain the behavior and properties of gases. And what you'll find is that most of the time the predictions are correct. Now, if they are not perfectly correct, they are very close to being correct. Now that kind of tells you something important about the postulates of kinetic molecular theory. What it tells you is that the postulates in the theory are pretty close to being exactly correct, but are not exactly correct. And this becomes important later when we're trying to understand how real gases sort of behave differently than the predicted properties we've been looking at before using the gas laws. And we'll talk more about that later. So the question is, what are the 5 assumptions or postulates of the kinetic molecular theory? So let me go over them right now. So the first postulate of kinetic molecular theory is that a gas is composed of molecules that are very far apart from one another. So let me talk a little bit about that. So let's say you were looking at a sample of the noble gas of argon. And so let's say we were able to look at this with a super powerful microscope. What would we see? So here we have an argon atom. So you might recall that because argon is a noble gas, it's only comprised of atoms and not several atoms stuck together. And so what kinetic molecular theory says is that the argon molecules, or atoms here, are far apart from each other. Now, we have some data that suggests that the distance between argon atoms at room temperature is about 3.3 picometers. So that's a very small distance. And so the way I sort of think about this is that if you have an argon atom, imagine it to be the size of a golf ball, the next golf ball argon atom would be about 4 feet away. So that gives you some idea how far apart gas molecules are. Okay, so the second postulate of kinetic molecular theory is that gas molecules, all of them possess a mass, but the volume is considered to be insignificant. So let me talk a little bit about that. So here in my picture of argon, here in this picture, we represent the molecule of argon here with a certain volume. And in fact, that is true. Atoms have a particular volume. Now, in kinetic molecular theory, we pretend something that's not quite true. We pretend that there really isn't too much volume to an atom or a molecule in a gas. So one way you can think about it is this, is that instead of having actual molecules with space, in kinetic molecular theory, we can think of these molecules as points. And so here are the argon atoms again, and these atoms have mass just like before, but now they have a very negligible volume. Again, we can just sort of think of the volume as points, but the distance between the atoms would be the same. Now, this has kind of important implications. And so one thing that we've noticed about kinetic molecular theory, it makes predictions that are not perfect, but are close to being perfect. And so one of the reasons why kinetic molecular theory is a little bit off in its prediction is because with the theory, we are making an assumption that is not exactly correct, and that these molecules don't have a lot of volume to one another. So the next postulate of kinetic molecular theory is that gas molecules are in constant motion in random directions, and that they frequently collide with one another. And then collisions between the molecules are said to be perfectly elastic. Now, what that means is that if you have two molecules of a gas collide, the total amount of energy before the collision will be the same as the total amount of energy after the collision. So let me give you an example of this elastic collision here. So here we have a gas molecule, and what it's doing is maybe this gas molecule is bouncing off another gas molecule like this. So here's the second gas molecule, and they're bouncing off. So let's say that the total energy of the gas molecules before they strike is maybe 1.00 joules. So what kinetic molecular theory says is that after the strike, they should have the same total of energy of 1.00 joules. So now this energy can be distributed a little bit differently between the molecules. So for example, maybe to start with this molecule on the left, it had 0.30 joules, for example, and this molecule on the right had 0.70 joules. And so after the strike, just as long as the total energy is the same, it may be distributed differently, but just as long as the total energy is the same. And so here maybe this some energy is being transferred from the molecule on the right to the molecule on the left, and so maybe now this molecule on the left now is up to 0.40 joules, and the molecule on the right is at 0.60 joules. And so still you can see that although there has been transfer energy from one molecule to another, the total energy before the strike is the same as after. And so that would be considered an elastic collision. Let me give you another example of an elastic collision. So let's say we have, say, the surface here of a beaker, for example. And so let's say we have here a molecule striking the surface of the beaker. And so maybe it has 1.00 joules of energy before the strike. And then what kinetic molecular theory says is that it should have exactly the same energy after the strike. And if so, this is said to be an elastic collision. Now, these are again examples of elastic collisions. Now, let me show you what really kind of happens. Instead, what really happens is that you have slightly inelastic collisions. So let me give you an example of that. So let's say, again, we're sort of looking at here a glass surface, and we're looking at a molecule that's striking the glass surface. And so maybe that molecule starts out with 1.00 joules of energy. Now, what might happen in reality is that after the strike, it might have just a smidgen less energy than it had to start with the strike. So maybe it might have only 0.98 joules of energy. So where did that extra 0.02 joules of energy go? Well, it may have been absorbed by the glass wall. So in this case, the collision is not an elastic collision. It is an inelastic collision. Here with this example here, it may be something like this. And so the molecules start out with the same energies that they had before, but maybe what you are able to see is that they have a tiny little bit less energy after the collision than what they had before. So this would be an example of inelastic collision. So you might wonder if these molecules here are striking and they're losing a little bit of energy, where is this energy going? And so the energy is thought to maybe leave the velocity part of the molecule and then enter in to other kinds of places in the molecule. So for example, that energy may go into the bond of the molecule. So for example, if you have a gas molecule that is diatomic, meaning it has two atoms stuck together, what you might expect normally is that those two atoms will vibrate against one another with a certain frequency. And so what could happen after the strike is some of the energy of translation here in the molecules is lost, is going into the vibrational energy of the molecule. So that is a possibility. So that is maybe one reason why these strikes could be inelastic. Anyway, kinetic molecular theory assumes that the strikes of the molecules are in fact elastic. Okay, so let's go on to the next postulate. The next postulate is that in kinetic molecular theory, we assume that there are no attractive or repulsive forces between atoms or molecules. Now, is this true? Yes, it largely is true, and the reason is because if there are repulsive and attractive forces between molecules, they only occur when the molecules are extremely close to one another, and the attractive and repulsive forces are very, very small. So kinetic molecular theory is pretty accurate because here we're assuming that all the molecules are far apart from one another. However, what you might be able to imagine is a situation when the molecules may be for some reason relatively close to one another, and if they're relatively close to one another, then maybe the attractive repulsive forces might affect the predictions that you would make from kinetic molecular theory. The final postulate of kinetic molecular theory is that the kinetic energy of molecules is directly proportional to the temperature. So if you have a gas, call it A, of a certain temperature, let's say it's like 300 degrees Kelvin, it is going to have in total a certain amount of kinetic energy. If you have a gas B of the same temperature, again 300 degrees Kelvin, it's going to have exactly the same kinetic energy. And the higher the temperature of the samples of the gas, the greater kinetic energy it will have. And so there's actually a formula that you can use where you can take the temperature of a gas sample and figure out what the average kinetic energy in joules of that sample of gas is. And so that formula is there, in that the kinetic energy average of the molecules is equal to 3/2 times R, the gas constant, times temperature. And I don't think you really need to know that formula for now, but just remember that the kinetic energy value of a gas is proportional to the temperature of a gas. So now what I want to do is I want to go through a few of these postulates of kinetic molecular theory and then from them make predictions of the properties of gases. And so what we find overall is that the postulates of kinetic molecular theory are excellent at predicting the behavior of all these gas properties and gas laws. So if that is the case, that suggests to you that the postulates of kinetic molecular theory, the 5 ones that I just went over, are basically right. So what I want to now do is go to the computer and just describe a few of these postulates here. So what I want to do is go over how certain kinetic molecular theory postulates explain certain properties. So I'll go over how the KMT postulates explain pressure, compressibility, Boyle's law, Amonton's law, and Dalton's law of pressures. So one of the postulates of kinetic molecular theory is that gas molecules are constantly moving around. As I recall, that's assumption number 3. Now we can make a prediction from this. Because gas molecules are always moving around, and because they individually have mass, we would predict that if they strike a surface, that surface is going to feel a force from those gas molecules. And so that force over a certain area is going to amount to a certain pressure that these gas molecules have. So in short, one of the postulates of KMT theory predicts is that gases will have pressure. So we can extend that a little bit more by predicting that if we increase the number of moles of a gas, if we want to keep that gas at the same pressure, we're going to have to also increase the volume of the gas. And so we sort of have an example of that here. So we have a certain amount of gas with a certain number of moles. Here it looks like 1 mole, and that this 1 mole of gas will have a certain pressure and occupies a certain volume here. Now, if you were to add more gas to it so that we have 2 moles, what you would find is the pressure would go up as expected if the volume was the same. But what we can do is to keep the pressure the same, we can expand the volume. So we would predict from KMT that if you double the moles of gas, you would double the volume, keeping the pressure the same. And so this relationship, this direct proportion between the moles of a gas and the volume of a gas, is Avogadro's law. Okay, so let's look at another way that a KMT assumption predicts the properties of a gas. So one of the postulates you might remember about KMT theory is that there's a lot of empty space between gas molecules. And so this was assumption number 1. So from this assumption of KMT, we can predict one of the properties of gases, that is of compressibilities. So it just kind of makes sense if there's a lot of space between the molecules, as the assumption suggests, that we should be able to push the molecules in closer to one another and compress them. And so because KMT says that there is a lot of space between molecules, we would expect that if we have the volume of the gas, because you can sort of squeeze the molecules together while you're having the volume, you should double the pressure of the gas. And again, this is a prediction that is made straight out of the assumption of KMT, and so this, having the volume of the gas and doubling the pressure, is Boyle's law. So again, the assumptions of KMT predict a gas law here, which is Boyle's law. Okay, another thing that kinetic molecular theory can do is it can predict the gas property of Dalton's laws of partial pressure. So first, let me remind you what Dalton's law of partial pressure is. What Dalton's law of partial pressure tells us is that the pressure of a mixture of gases is equal to the individual partial pressure of gases in the mixture. Now, one of the assumptions that KMT makes is that there are no attractive or repulsive forces between the molecules of a gas. And so from this, we can make a prediction. This prediction would be that when you add gases together to be in the same volume, because the gas molecules are not interacting with one another, then you should be able to simply add the pressures together to find the total pressure of the gas. Now, let's just say for a moment that maybe the molecules were strongly attracted to one another. What would happen then? Well, if we added those molecules together, then what might happen is that the total pressure might end up being less than the two pressures added together. And we don't see that. We see in general Dalton's law is fulfilled, that the total pressure of a gas is the same as the individual pressures of the gases you mix together. Now, there are some other ways that the postulates of kinetic molecular theory explain the gas properties. So here I have an example of how a postulate of kinetic molecular theory helps explain the properties that a gas has an indefinite shape and an indefinite volume, and so I encourage you to go over that. And then here I have another slide which continues to show that you can use the postulates of kinetic molecular theory to predict Charles' law, so I encourage you to go over that. So thank you for listening to this presentation, and we will see you next time.